The last lecture I explained epsilon net theorem, but I did not explain how to connect the epsilon net theorem to PAC learning. So I'm very happy there are some students who have some curious about how to connect epsilon net theorem to PAC learning. So this video I will explain how to connect them. Okay, so let's review how to define hypothesis as a set. So we are now considering a binary classifications, which means each hypothesis mapping every input to a label either 0 or 1. So when we have a finite training data point, among the training data point, there are data point that have value 0 as the output label, and there are some point that have value 1 as the output. So when we collect the element having positive response, and we can think the hypothesis as the set of element having the positive response. So for instance, in this case, the H hypothesis can be considered as a set which consists of these three positive responses. Indeed, the hypothesis we are considering have infinite element. So it can be function on continuous input domain. So for instance, in 2D real space, we can define a hypothesis which define a boundary where this area always positive response, this area always negative, always 0 response there. Then by random selection on training data sample or data set S, when the randomly generated data located in this area, all these points will have positive response. So the hypothesis H define the boundary will construct a set having positive response, which is subset of training set S. Okay, so in that way we can define every hypothesis as a set. But note that in this definition, basically, although we have two different hypotheses, when the training data point are not located here, then the two response from this hypothesis and this hypothesis H prime are the same. H also have positive data point here, and H prime also positive data point here. Okay, so with finite data point, even with continuous hypothesis class, we can have at most this amount of hypothesis from n training data point. Okay, when we consider this H prime are the same hypothesis because they have the same response for this n training data point, then we can count at most this amount of different hypotheses from n training data point, even if we have continuous infinitely many hypotheses for continuous input domain. That is Sauer's lemma. Okay, so when we have d VC dimension, among 2 to the d number 2 to the n possible mapping from n data point to binary class, we can define at most n choose less than or equal to D, which is basically N0 plus N1 D. This amount of hypothesis at most when we have VC dimension D. Right? Okay. So now I will explain how to connect our hypothesis analysis, so the epsilon net theorem to PAC learning argument. So this lemma will connect them. So let H prime a new hypothesis class, which is defined as the set difference between any hypothesis and a given hypothesis. It can be any set or it can be any hypothesis. So it can be H star, the ground truth hypothesis. So let's say C star is equal to H star, the ground truth hypothesis that define the true operable. Then let H prime be the collection of error region of hypothesis in H, because that is just set difference between the ground truth hypothesis and our hypothesis H. Then the VC dimension of H prime is equal to that of H, and they share their shatter function because they share the same VC dimension. How to show this lemma? It is pretty simple. For any set A, B, C, we have this property, set difference A and C. When we have a set difference A and C equal to set difference between B and C, then A equal to B, and the reverse also hold. From this fact, we have the following two important things. For all hypotheses, we can define a bijection mapping between H and H prime like this. Okay. Because when H prime is not the same, then H set difference C star is not equal to H prime set difference C star. If they are the same, then this was the same from this fact. The second fact is this. For every H and H prime belong to our hypothesis class, H intersect A and H prime intersect A when they are the same. This is if and only if H intersect A set difference C star intersect A equal to H prime intersect A set difference C star intersect A. That again, we use this fact. And with a simple calculation, we can easily check that this is exactly the same with this, and this is exactly the same with this. Okay, so in the end, H intersect A is equal to H prime intersect A if and only if H set difference C star intersect A equal to H prime set difference C star intersect A. Therefore, for any given set A, the number of hypotheses defined on set A is equal to the number of hypotheses H star defined on A. So when one of H and H star can shatter the set A, then the other set system can also shatter A, since the HA can shatter A means the number of HA, number of element in HA is equal to 2 to the cardinality of A. And we also know that the cardinality of HA and cardinality of H prime A, so which also means H prime A cardinality also 2 to the cardinality A. Which means H prime A can also shatter A, which means H and H prime share the same VC dimension, right? So why this lemma is useful? So basically from H prime and the theorem we obtain here, we can conclude this theorem for any collection hypothesis class H and distribution D. If a training sample S is drawn from distribution D of size n that satisfying these two conditions, from the lemma and theorem we just derived, with probability greater than 1 minus delta and is 1 minus delta, every hypothesis H with true error greater than or equal to epsilon has non-zero training error, which means every hypothesis H with training error equal to 0 has test error less than epsilon. So we have epsilon delta PAC learning property with this amount of samples. So we just found the sample complexity for hypothesis class having VC dimension D. Right.